Hello students, welcome back. In this video we're going through chapter 11, section 2, contingency tables. So for the key concept here is that we are now going to consider methods for analyzing contingency tables, which include frequency counts for categorical data arranged in a 2x2 table. So we are presenting a method for conducting a hypothesis test of the null hypothesis and that the row and column variables are independent of each other. So in simpler terms, we are having sets of data. And from those sets, we are going to analyze it to see how independent or how dependent and related those sets of data are. So we are going to be doing 3 different methods: test of homogeneity, Fisher's exact test, and Namir's test for matched pairs. Okay, so to continue on contingency tables. Like we said in the previous slide, it is a two-way frequency table consisting of frequency counts. One variable is used to categorize rows and the second to categorize columns. And we are conducting tests of independence. So we will test the null hypothesis as well. So the objective here is we will conduct a hypothesis test of independence between the row variable and the column variable in a contingency table. To go through the notation, O is the observed frequency, E is the expected frequency, R represents the number of rows, not including labels or things like that, so rows of data, and C represents the number of columns. Again, just not counting the titles of it. So the requirements is that random sample, it must be arranged in a two-way table, and that the expected frequency is at least 5. Notice how it's not you have to have 5 observed frequencies, but the expected frequencies need to be at least 5. So we will have the hypothesis test be conducted where the null hypothesis is that the row and column variables are independent, which would make the complement of that alternative, H1, that the row and column variables are dependent. Since we are doing a hypothesis test, we need a test statistic. So once again, similar to the previous section, we will let the test statistic be chi-squared equals the summation of the value of O minus E quantity squared divided by E, where O is the observed frequency in a cell and E is the expected frequency in a cell. And E is found by doing the row total multiplied by the column total divided by the grand total. P values are provided by technology again, or by table A4. Critical values, this is where it's a little different from what we've done. The critical values are found in table A4, but the degrees of freedom is going to be the value of R minus 1 multiplied by the value of the number of columns minus 1. And once again, since we are doing tests of independence with contingency tables, they are always right-tailed. So we are not interested in the chi-squared L quantity, only the right tail. So here's the relationships. A very similar chart appeared in chapter 11, section 1. So if the O's and the E's are close, then we have a large p-value, meaning we are in this region over here. And the conclusion is we fail to reject independence. And if the O's and E's are far apart, we are in this region over here. And from that, we conclude that we reject independence. So let's do a quick example about finding expected frequencies. So the table on the next slide is a contingency table with 4 rows and 2 columns. The cells of the table contain frequency counts. The frequency counts are the observed values. So the expected values are shown in parentheses, and we're going to show how we get that. So the row variable identifies the treatment used for a stress fracture in a foot bone, and the column variable identifies the outcome of a success or failure. Refer to the table and find the expected frequency for the cell in the first row and the first column, where the observed frequency is 54. All right, a lot of words, so let's look at it. Basically, if someone has a fracture, they are saying that there are 4 different types of treatment. You can do surgery, a weight-bearing cast, a non-weight-bearing cast for 6 weeks, and a non-weight-bearing cast for less than 6 weeks. And for each of these, there are successes or failures of the treatment. So for a surgery, 54 people had a successful surgery, 12 had an unsuccessful surgery or a failure, and so on. So these values outside of parentheses are the actual number, that's the observed frequency, and E is the expected. So how do we get those expecteds? Well, it's the row total multiplied by the column total divided by grand total. So the first cell in the first row with a total frequency of 66 and the first column with a total frequency of 182. So where that come from? 54 plus 12 is 66. The column total is going to be 54 plus 41 plus 70 plus 17 is 182. Add those two together is 253. So do the calculation, and then you get your expected frequency. So repeat that process for all of them. So the interpretation. We can interpret the expected value by stating that if we assume that success is independent of the treatment, then we expect to find that 47.478 of the subjects would be treated with surgery and that the treatment would be successful. So that would mean that we would expect the value right here to be exactly or very, very close to the expected value. It's a little bit more. So there's obviously a discrepancy between the observed of 54 and the expected of 47.478. And such discrepancies are key components of the test statistic that is a collective measure of the overall disagreement. Basically, how much do those two values, O and E, vary? Okay, let's go on to a more thorough example. That one was just really showing you how to find O and E. So use the sample data from the previous example with a 0.05 significance level to test the claim that success of the treatment is independent of the type of treatment. So what does the result indicate about the increasing trend to use surgery after a fracture? First, check the requirements. We are good. So the null hypothesis is, again, that they are independent of the treatment. H1 suggests that success and the treatment are dependent. Significance level, we'll do alpha is 0.05. So we will find our chi-squared value with a test statistic. So we have our chi-squared is 58.393 using that equation, or we can use, you guessed it, StatCrunch, or really any of the other technologies. So here is our procedure. So we are going to quickly fill in that chart. Notice how I included variable 1, which is the name of the description. So we're going, once we have this chart filled in, we're going to click Stat, Tables, Contingency, and we are actually doing it with summary. We're not giving individual data points. We are giving a summary of all the data and listing in that two-way table. So we're going to do it with the summary. Once we are there, we're going to follow these steps. So for the columns, select the columns of data to be included in the analysis. So when we select the columns, we're going to do variable 1 and variable 2, which are these two columns right here. Remember, just hit Shift or Control to highlight both of those. And then for the row labels, this is why we have to type this in. We want the row label to be variable 1. That describes the 4 different types of treatment available. The hypothesis test we're doing is a chi-square test for independence. Notice these are the other ones that I mentioned we will do later, so just keep those in mind. It'll be the same process, only you'll be doing these different tests for the type of problem that calls for it. Once we do that, we do compute, and this is what the computer spits out. It gives us our degrees of freedom of 3, our chi-square value, and our p-value. So 58.39, how does that compare? And it is exactly the same as what we got. Notice this is a summation of all of them. So this is the one that we did in the top left, but you have to add the values of all, I guess there's 8 total cells that we have to add together. So the sum of all of them is 58.393. So you can just get an idea of how brutal this would be to do by hand with the calculator. Fortunately, we have technology. Okay. The book provides all these steps on page 555 as well. So if you were to do this with table A4, you can get the degrees of freedom by doing the number of rows minus 1 multiplied by the number of columns minus 1, which is 4 minus 1 times 2 minus 1. So 3 times 1 is 3. And the test statistic of chi squared is 58.393. And since that exceeds the highest value in table A4, we know that the p-value is going to be smaller than 0.005. And since the p-value is less than 0.05, what does that mean? We reject the null hypothesis of independence between source and treatment. If we were doing it with the critical value, not the p-value, we would look at the critical value from the table, and with our significance level and our degrees of freedom, we would compare and contrast the two. So we have our critical value of 7.815. Our test value is way out yonder. So because we are in the green critical region, we reject the null hypothesis. Same conclusion. So it appears that success is dependent on the treatment. Although the results of this test do not tell us which treatment is the best, we can see that the success rates of 81.8, 44.6, 95.9, and 77.3 suggest that the best treatment is to use a non-weight-bearing cast for 6 weeks. The results suggest that the increased use of surgery is a treatment strategy that is not supported by the evidence. So this is saying they are dependent on one another, success, but if we were to look just at the success and failure rates, that would suggest that the non-weight-bearing treatment for 6 weeks would be the highest probability of getting a successful treatment for your fracture. Okay, so chi-square test of homogeneity. And this is the test of the claim that different populations have the same proportions of some characteristics. So in a typical test of independence, sample subjects are randomly selected from one population, and values of two different variables are observed. So we're taking a population, and people are randomly selected from that population, and then two different variables are being observed within those same people. So let's look at a good example. So the procedure would be that we are doing the same notation requirements, test statistics, critical values as before, but instead of testing the null hypothesis of independence, we test the null hypothesis that the different populations have the same proportion. Okay, note the difference. So let's look at an example. I think it's a pretty cool one. So Reader's Digest had an experiment in which 12 wallets were intentionally lost in 16 different cities. So we use a significance level of alpha is 0.05, and we want to test the null hypothesis that the cities have the same proportion of returned wallets. So here is our data. They don't tell you what each city is, so we'll call it city A, B, C, D, E, F, G, all the way up to P. So of the 12 wallets, in city A, 8 were returned, 4 were not. In city J, for example, only 1 wallet was returned, and 11 were not, etc. So we want to know, given this, do the cities have the same proportion of returned wallets? And at a quick glance, you can probably say, well, no. I mean, this city has 11 returned, this one has 1 returned, but let's just humor myself and the author and go through it. So the null hypothesis is H0, which says that whether a lost wallet is returned is independent of the city in which it was lost. The alternative is that a lost wallet being returned depends on the city in which it was lost. Okay, so that should kind of add some clarity to what we mean by independence and the two variables. So step 1, always check the requirements. They are satisfied. So now we will use StatCrunch to be able to do the test. So the chi-squared value is equal to 35.388, and the p-value is 0.002, which is rounded. Because the p-value of 0.002 is less than 0.05, we reject the null hypothesis. Let me show you how to do that with StatCrunch. So I have to type in, a lot of typing, but variable 1 is the name of all the different cities, A through P. And variable 2 is how many were returned. Variable 3, how many wallets were not returned. Once I do that, we go back to stat, tables, contingency, with summary. Again, we select the two columns for variable 2 and variable 3. The row labels is variable 1, and we are doing a chi-square test for independence, compute, and we have our p-value and our value of the chi-squared right here. So we reject the null hypothesis of independence, so it appears that the proportion of returned wallets depends on the city in which they were lost. There is sufficient evidence to conclude that the proportion of returned wallets is not the same in those 16 different cities. So we also are going to be doing Fisher's exact test. So in this case, every cell must have an expected frequency of at least 5. Fisher's exact test is often used for a 2x2 contingency table, and this provides an exact p-values. So for this, it is a good idea to use technology. So Mythbusters show a pretty funny show. I'm sure you guys have seen it. And we want to know, you guys might have heard that yawns are contagious. Well, they did a test on that. So there's different outcomes. So the subject exposed to yawning, yes. And then did the subject end up yawning when they were exposed to yawning? 10 were yes, 24 were no. And then the opposite is true. Was the subject exposed to seeing someone yawn? No. Did the subject yawn? Yes. And then this is the other case. It's almost like a Punnett square where it's both no, no. So using the Fisher's exact test results in a p-value of 0.513. So there is not sufficient evidence to support the myth that people exposed to yawning actually yawn more than those not exposed to yawning. And the Fisher's exact test, if you go back over here, is one of the options right there. So just make sure you do that with the proper data input. McNemer's test for matched pairs. So now we are dealing with for 2x2 tables consisting of frequency counts that result from matched pairs. The frequency counts within each matched pairs are not independent, and for such cases, we can use this test of the null hypothesis. So let's look at an example. Here is our test statistic for these types of problems. Again, here's your Punnett square, if you would, of treatment X and then cured when compared with treatment Y. So here's your B, your C values. Just kind of see where this test statistic equation comes from. So are hip protectors effective? So a randomized control trial was designed to test the effectiveness of hip protectors in preventing hip fractures in the elderly. Nursing home residents each wore protection on one hip and not the other. So let's look at what the data said. So no hip protection worn and no hip fracture. And then here are your 4 outcomes. So here is where you have hip protector worn and then no hip fracture. 309 people. And here's all the rest of the data for that. So if you do your calculation with your test statistic, you get a chi-squared value of 0.640. So with a 0.05 significance level and degrees of freedom given by df equals 1, which is the 2 minus 1 times 2 minus 1, we refer table A4 to find the critical value of chi-squared is 3.841 for this right tail test. Our test statistic of 0.640 does not exceed that critical value, so we fail to reject the null hypothesis. That includes Chapter 11, Section 2. Thank you.